the most important concepts in all of mathematics is the concept of a function. And so central to the covering of trigonometry, we got to understand what a function is and a lot of the different terminology that goes along with a function. So in this lecture, we're going to be looking at what is a function, the definition of functions. What do we mean by the domain and range of a function? What are some properties that we can determine about a function? And then we're going to look at a library of some useful functions that we'll need to be familiar with as we go forward. And then one last concept, which you may or may not have had any experience with before, but we're going to throw it in anyways, is look at piecewise defined functions. Now, the basic concept of a function is pretty simple. Think of it as this giant black box where this box is my function f, and there is a little input valve right up here where you can put things into it. All right, you put an input in right there, and you don't really know what happens inside of this machine, but once it goes in there, something cranks away, and then you have out the other end comes an output. Okay, so this is the basic concept of a function. You throw something into it, it does something to whatever you put in, and then you get something out of it. Okay? Now in mathematics, what do we put in? We generally put in numbers into a function and out come another number. Okay? We often work with functions that are formulas, but you can think of functions in terms of tables and graphs and formulas. But we can actually, with formulas, we can plug in other variables. We can plug in other expressions into them. Something happens inside the function, and then out comes something new. Okay? So an informal definition might be that a function is some kind of rule or mapping that takes an input and turns it into an output. Now we will, like I said, look at probably 3 different more common ways of dealing with these. We talk about a function in terms of a table of values. What I mean by a table of values is you have an x and a y. And so a list of values here, you plug those in, you get the values y that go along with those. That is a function. A graph can be thought of as a function, although we'll talk about some pictures that do not represent functions and some that do. What we mean by there is, of course, our x-axis is our horizontal and our y-axis. The height at any point here, that's my little curly brace, sorry. Boom, the height here is going to be the function. And then we can do a formula like f of x equals 6x plus 2. We'll talk a little bit more about all 3 cases here in just a moment. Now, in order for a graph to be a function, we have to have a property that is satisfied by this statement right here. It's the most important property of a function. Okay, it's the function property that says each input produces exactly one output. Now that output doesn't have to be unique. It's not necessarily a unique output, meaning you could put in the number 3 into a function, and 3, after it cranks away inside the function, produces the number 7. So 3 turns into 7. You could also have a 4 thrown in there and also turn into 7. That's just fine. What you can't have happen, so this is okay, this is okay. What's not okay is if 3, you throw 3 in and you get a 7 and you also get an 8 out of it. That you can't have happen. That is, you cannot have multiple outputs for a single input. But what you can have is one output produces an output, one output produces an output, even if they're the same output. And they can be different as well. Okay? The way that you check that with a graph is what's called the vertical line test. The vertical line test is a way for us to determine by looking at a picture whether or not the function represented by that graph is in fact a function. So no vertical line can pass through more than one point of the curve. Okay? So let's consider 2 pictures here. Let's draw 2 graphs. One is a function, one is not a function. Vertical line test says what I'm going to do is I'm going to draw or consider what vertical lines would do if I drew them on this graph. So here's a vertical line. Any vertical line I draw, how many times does it hit? Okay, that means it's a function. On the other hand, this one hits once right there, but if I draw a vertical line right here, how many times does that hit the curve? More than once. If anywhere at all a vertical line crosses more than once, that means it's not a function. Notice how there is a place where it crosses only once, but there is also a place where it crosses more than once. Anytime that happens, you have something that's not a function. Now let's talk some terminology. The domain of a function is the set of all possible inputs. So you think of domain in terms of its English definition, meaning, you know, the so the domain of a country is everywhere that country has influence or rule. The domain of a king is everywhere that he rules over. The domain of a function is everywhere that all the inputs that it rules over, meaning everything that its rule applies to. Anything you can plug into that function is going to be in the domain of that function. So some functions like x plus 2, you think about that, there are no exceptions to what you can plug in for x, right? What can I plug in? That's the real question of the domain. And in this case, we can use this notation for all real numbers. On the other hand, the second function that I have listed here is 1 over x. There is one number that you plug into that would be a problem. The number 0. You can't divide by 0. So this right here has a domain of everything except 0. Now I can write that a couple of different ways. I could write it as all real numbers except the set of 0. Or I could write it in interval notation saying it goes from negative infinity all the way up to 0, but not including it, and from 0 up to positive infinity, but not including 0. That's our interval notation. On the last one, the new problem is the square root. What are we allowed to plug into a square root? Or I guess another question is, what are we not allowed to plug in? And as long as we're restricting ourselves to thinking about real valued functions, which for the majority of this for the majority of this lecture series, that's what we're going to be doing, then we can't plug in negatives inside. Okay, no negatives. This one had no zeros in the denominator. So if there's no negatives inside the square root, that means 3x minus 2 has to be greater than or equal to, 0 is okay, 0. And if you solve this linear inequality by moving the 2 to the other side and divide by 3, you end up with x has to be bigger than or equal to 2 thirds. 2, move to the other side, and then you divide the 3 across, so 2 thirds. Okay? Or in interval notation, that means start at 2 thirds and anything all the way up to positive infinity would be okay. That's the domain of a function. Now the range of a function just means everything that comes out of the function. Okay? So domain is everything that goes in. Range is everything that comes out. Okay? So take a look at this picture that I've got drawn here. You've got a function g that follows this path, and you got a function f that follows this path. Let's talk about the domain of f. What are the numbers that you can plug in to f? That's, by the way, horizontal. So if you want to talk domain, you're talking what's the range across the x-axis over which the curve f is defined. And notice, because it's got closed points at the end, you can start at 4 and then at negative 4 and end at positive 4. So negative 4 to positive 4, I use brackets to include those numbers. Now what's the range of f? Well, the range of f is going to be everything that is up and down. Okay? How far does it go? Well, it starts here and goes up to right there. Okay? So the lowest value on the y-axis is -3. Those are the outputs of this function. So from -3 to +5. Okay, now we can use the same reasoning for g. Notice how the domain of g is going to be from -3 to +3, and the range of g is going to be where it goes vertically. So the lowest point on g is down here at -4, and the highest point is up here at +4. Now, it doesn't necessarily mean that what happens at the endpoints with my two functions. What it does mean is what's the highest and the lowest point. The highest value that it goes to was 4. The lowest was -4. And so there's your domain and range of g. All right, now let's take the formula case for a function. A function can be defined in terms of a formula, and this is the way that we would write it. For a function f defined by f parentheses x, we read this as f of x equals x squared plus 7. What we mean by f of x is f applied to any number x, the output should be x squared plus 7. So in this notation, x is the input, x squared plus 7 is the output. So f of -6 would be -6 squared plus 7. You plug in the -6 anywhere there is an x. So you get 36 plus 7, which is 43. All right, f of 3a. That means plug in a 3a everywhere there's an x, so you get 3a quantity squared plus 7, or 9a squared plus 7, which we can't simplify any further. You can even do it with expressions. So we've plugged in a number, we've plugged in a variable. We can also plug in a binomial in this case. So that's b minus 1 squared plus 7. Notice I just replaced the x with the input. And we can multiply that out. Remember to FOIL whenever you have a binomial squared. That means b squared minus 2b plus 1 plus 7, or b squared minus 2b plus 8 is the output when you plug b minus 1 into this function. And we can also graph using value tables. So the graph of a function, once we have a formula, is simply done by plugging in different values of x into your function and seeing what the output would be. If you plug in -2, you end up with 4 plus 7, which is 11. Plug in a -1 plus 7, or -1 squared plus 7 gives me an 8. 0 squared plus 7 gives me 7. 1 squared plus 7 gives me 8. And 2 squared plus 7 gives me 11. All just plugging in different values of x. Then we go plot those points and sketch the graph. So at -1, -2, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 up here. And then at -1 we're at 8, so 1, 2, 3, 4, 5, 6, 7, 8 right here. And then 7, 8, and 11. 1, 2. And the shape, of course, we recognize as our parabola. But the point being now that, in this case, instead of having y equals x squared plus 7 that we've graphed before, you can do it as a function. Let's consider the function in the graph below. Our goal is to obtain information about a function from its graph. So to begin with, question A says, what are f of 0, f of 3 pi over 2, and f of 3 pi? Remember that a function's output is the height of the graph at the input value. Alright, so this is the input axis. This is the output axis. X is the input, y is the output. So f of 0 means go to x equals 0. What's the height? F of 0 is 4. f of 3 pi over 2. So go to 3 pi over 2, which is right here. The height is 0. And f of 3 pi, which is at 3 pi right here, is negative 4. Notice how, again, the x value in a coordinate is also what's being plugged in, and the y value is the output. Now, what's the range of the function as it's drawn here? Sorry, what's the domain of the function as it's drawn here? Remember, domain is how far does this thing cover on the x-axis. Starts here, goes all the way to here, which we're told is an x-coordinate of 4 pi. So the the domain is from 0 to 4 pi. Oh, and it's inclusive because you got points at the end. What's the range? Since it goes all the way down to negative 4 and all the way up to positive 4, that's going to give us our range. So from negative 4 to positive 4. The next question is to list all of the intercepts for this. Now you'll still have the graph on your notes there. I tell you, pull that back up just a little bit there. All right, so the intercepts. So what are the x-intercepts? Where does this thing cross the x-axis? It's pi over 2 comma 0. It's at 3 pi over 2 comma 0. It crosses here at 5 pi over 2 comma 0 and 7 pi over 2 comma 0. The only y-intercept, of course, and by the way, a function can have only one y-intercept since it passes the vertical line test, is 0 comma 4. Next question. How often does the line y equal 2 intersect this graph? So the line y equal 2, you'll recall, is a horizontal line with a height of 2. So how many times does it cross the graph? 1, 2, 3, 4 times. Now up here on part A, we asked the question, if I knew the input, can you tell me the output? What if I give you the output? F of negative 4. Sorry, f of x is negative 4. Right? Negative 4 is this height down here. There are 2 answers, right? So x equals pi or 3 pi. Both give me an answer to when is f of x equal to negative 4. Question G asks us, when is f of x positive? When is it greater than 0? The function is positive above the x-axis. That is, for any height that's positive. So where on the x-axis, and I'll do this in green, do we have values that are greater than 0? Well, up here, right? This one, and up here, and right here. Now, what values of x is that? Well, it's everything from here up to, but by the way, not including pi over 2. It's from 3 pi over 2 to 5 pi over 2. Why not including? Because I say strictly greater than, and then over here. So if you write that in terms of intervals, what you end up with is it starts at x equals 0, ends up at pi over 2, but not including, jumps over 2. By the way, the U stands for union. 3 pi over 2, all the way to 5 pi over 2. I'm just talking about ranges of x's, not points now. These aren't coordinates. These are an interval. And then from 7 pi over 2 all the way up to 4 pi inclusive. 4 pi being the x value, right, of that point right there. Now the last question jumps off the screen here, so let me scroll down and then we'll scroll back up if we. When is it increasing? When is it decreasing? So increasing. When is it going uphill? It's going uphill from there to there and from there to there. Right, which is a value from pi to 2 pi and 3 pi to 4 pi. So increasing from pi to 2 pi and from 3 pi to 4 pi. When is it going downhill? All right, so it's going to go downhill on, I'm going to have to, I've run out of colors here, right here and right here. Okay, that's where it's decreasing, which means from 0 to pi and from 2 pi to 3 pi. These are all answers we're able to get from just looking at the graph. We've got some more terminology in this lecture. At this point, we are going to define some new properties of a function. A function is said to be even if for every number x in its domain, if you were to plug in negative x, it's in the domain and you get the same answer. F at negative x is the same thing as f of x. Okay, that makes something an even function. What does that mean if you look at the graph? Well, let's say a function does this over here on the right-hand side. So at this value x, if you were to go over the same distance but to the left, you should be at the same height as you are for this function. And in fact, that's true for all x. So basically an even function has the y-axis as a mirror. It's symmetric about the y-axis. On the other hand, a function can be called odd if you still can plug in negative x for every x, but what you actually get is a negative of the original function value. So what that looks like on a graph is, say this function does this over here. Over on this side, if you go from here to negative x, this was the height at f of at x, that's f of x. That means you're going to be a negative that same height. And if that's true for every function, then what it is you've got a mirror here and then a reflection about the x-axis. So you mirror it across the y-axis and then reflect it about the x-axis. Same idea. Reflect, 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 mirror, mirror. So you flip it both times. Okay. Now all even functions, I already said this earlier, but they have a graph that is symmetric about the y-axis. Okay, so this one right here is clearly even, and this one right here is not even. And you can tell just by looking at the graph. There's another way to tell whether or not a function is odd or even. That's by looking at the function formula itself. So let's do that. In order to determine whether or not a function is odd, even, or neither, you can plug in negative x to see what you get after you simplify. Okay? So, for example, f of negative x here would mean negative x squared minus 5. Okay? Plugging that in, simplifying, which gives me x squared minus 5, notice that's the same thing as the original function, x squared minus 5. So you have f of x. If f of minus x equals f of x, then it's called even. Just takes a little bit of algebra simplifying, right? The algebraic simplification. Now f of negative x here would give me 5 times negative x cubed minus a minus x. Remember, to plug in a value into your function means to substitute it in for all the variables that you see in the problem. So I'm replacing all the x's with negative x's. Now what is negative x cubed? Well, if you cube the negative, you get a negative. If you cube the x, you get x cubed. So I'm just going to put that negative out front. I've got a minus 5x cubed. And minus and minus here makes plus x. Now how is that related to the original function? Well, notice if I factor out a negative, I have a 5x cubed minus x, which is in fact negative f of x. So f of x, or minus x, equals negative f of x, which means that function is odd. Another important concept when we work with functions is to talk about the average rate of change of a function. So that's how much the function changes with respect to the input variable. Rates of change can be thought of in terms of, say, speed or velocity. If your function represents a position of a particular particle or a position of an object, then the average rate of change would mean how fast that position was changing over time. Now, if we want to find the average change over two input values, then what we do is we use a formula. The average rate of change from A to B is given by the change in the function, so f of b minus f of a, divided by the change in the input values. Which kind of makes sense. If you think of, again, let's say f is a length or distance, and let's say x is time, just as a sample, then rate of change means change in distance over time, which is exactly a formula that we're probably all familiar with. Miles per hour would be a rate of change if your f measured miles and your x measured hours. But that concept can be generalized to all functions, and we can just look at a function and say, what's the average rate of change of that function as we move from the value x equals 1 to x equals 5? Well, we got to know f of 5, which is 3 times 5 squared, which is 3 times 25, or 75. We got to know f of 1, which is 3 times 1 squared, which is 3 times 1, or 3. Then we can use our formula, f of b minus f of a over b minus a. So that's 75 minus 3 over a and b now are 1 and 5, so 5 minus 1, that's 72 over 4, or 18. The average value of change, or sorry, average rate of change of that function is 18. Okie dokie. Now let's take a look at some of our parent functions. So I want us to go through, just so that we're familiar with them as we need them throughout the rest of the course, of some of our more basic types of functions that we need to be familiar with. I'm going to go through these relatively quickly in order just to cover them all. You're more than welcome to take a moment and pause between them to give them some thought, or to listen to and repeat some of this if we go too quickly. But the simple functions that we start with are the simplest possible kind of function would be the constant function. What is a constant function? Is a function that no matter what input you give it, the output is always the same. And that graphs as a straight or horizontal line. Now this looks just like y is equal to b, which we know is, as a line, a horizontal line whose height is at y equals b. The next simplest function is the identity function, which means the input equals the output. Now that's the function f of x equals x, right? If I plug in 2, I get 2. If I plug in 3, I get 3. So it's the simplest type of black box function that you're throwing something in, you're getting exactly the same thing out. And graphs just like this for diagonal on the Cartesian coordinate system. Linear functions are also lines, but we can move them around a little bit. We can change their slope or their slant, and we can also change where they are located on the plane. The general form for a linear function is f of x is equal to mx plus b, where m and b are real numbers. You've seen this before somewhere in your mathematics, and m is a concept known as slope, which, by the way, slope is also the same thing as rate of change, which we just discussed earlier. So the rate of change of this function is the same actually all the way through. You'll find that for any linear function, the average rate of change doesn't change anywhere on this curve. B is the value where it crosses the y-axis, so we're going to call that the y-intercept form of a linear function. All right, we've graphed this one in our lecture series already, but f of x equals x squared has the shape of a parabola. All right, and you can get that by just plugging those numbers in. So this parabola is very familiar to us. We can generalize the parabola by moving it around, changing how narrow or skinny it is, but this is the parent function for that particular type of graph. The cube function basically looks what's very similar to a parabola, in which you break the piece on the left-hand side and flip it down. So you end up with something that looks like this shape, although actually it's a little bit flatter than a parabola down here in this region, and steeper, climbs faster than a parabola. A square root function, f of x equals square root of x, is like a parabola that's laid down on its side. However, notice it's not the parabola with both the top and the bottom. And the reason why is that this right here makes it fail the vertical line test. That's not a function. But when you talk about the square root of x, you're always talking about the positive number that when squared gives you x. So it's always just the upper half of this curve is what the graph of square root of x looks like. Now the cube root function, if you have f of x is equal to the cube root of x, actually is the full graph of the x cubed, where you rotate it about the line y equals x. You basically take the picture here for x cubed, pick it up, and flip it along that diagonal, and you'll end up with this graph right here. Okay? That's the cube root function. The reciprocal function, f of x equals 1 over x, has this shape right here. In fact, it has two pieces to it. It has a piece up here in the upper right quadrant, or quadrant 1, and a piece down here in the lower left quadrant. Notice, though, that this function is undefined for 0. You can't plug in 0. But as you get closer and closer to 0, notice the graph gets higher and higher and higher. But if you get closer and closer to 0 from the left-hand side, you get more and more negative, larger and larger negative numbers when you plug those in. So this is the shape of 1 over x. All right, the last of the functions that I want to take a close look at here in this lecture is the absolute value function. The absolute value function is the function f of x equals the absolute value of x. Now remember, what that really means is that if you have a positive x, like absolute value of 3 is just 3, what's the absolute value of negative 3? It's also positive 3. So if you look at all the positive values of x, notice how this line right here is just y equals x, or f of x equals x. Okay? On the other hand, we don't have that line extending off in this direction, because if I were to plug in this negative 3, I'm actually up here at a positive 3 as an output. So what happens is that if x is, say, positive, then f of x is equal to just x. On the other hand, what happens if x is negative? If I plug in a negative, you're always going to get the opposite of whatever x is, right? So over here, this graph right here is actually the graph of y is equal to negative x. And notice how this is an alternative way of writing down what the absolute value function would look like as a formula. You get x when x is positive, you get negative x when x is negative. That's what this graph looks like, but this also leads us to another concept of, can we have other types of functions that are different formulas depending on what the values of x that you're plugging in are? And the answer is yes. In fact, here is an example of a piecewise defined function. This says if your x is between negative 1 and positive 1, and including negative 1, use the formula negative x plus 1. If x is equal to 1, plug in 2, and if x is greater than 1, plug in to x squared. So it's it's defined in pieces. So that's why we call it piecewise defined function. So when you have a piecewise defined function, what you've got to do is you got to figure out which of my formulas apply for my input. F of 0. Where is f of 0 in this block of choices? Is it between -1 and +1? Is it equal to 1 or is it greater than 1? And the answer is it's this one right here. This is f of 0. So I would use -0 plus 1, or 1 is my output. What is f of 1? Well, here is the place where I use 1, so that means f of 1 has to be 2. And what is f of 2 then? Well, that's down here, so that's using 2 squared, or 4, and we can get our outputs that way. The next question is, what's the domain of that function? What are all the things that I can plug in? Well, I can plug in from -1, including 1, all the way up to +1, but not including it, but I can plug it in here, and then I can keep going anything bigger than that. So notice how, if you look at this on a real number line, I can start at -1, including here. I can go all the way up to 1, and then I can also include 1, and then I can go anything bigger than that. So what's my actual range, or sorry, my domain? It starts here and goes all the way to the right, which means it would be from -1 to +infinity, just like that. And the way that we graph a function like this is we graph each piece. Can I spell piece correctly? How about I-E-C-E? Each piece. So what you would do is separately graph what -x plus 1 looks like. Okay? So -x plus 1 as a function is, it has a y-intercept of 1. It has a negative slope, -1 slope, which means it's this line right here. Negative slope of 1. So this is my first piece. But where is that valid? It's only valid from -1 to +1, not including here. So I'll put a circle there. I'll put a dot here, and then I'll draw a line in between there. And the rest of this is not part of the function at all. What's the value at 1? It has a height of 2, so it's actually right there. As just a point. And then for everything bigger than that, it's a parabola x squared. Now what's the parabola x squared? Well, that's the function that looks like it starts here, goes up 1, and then it's up at 4 over here at 2. It's this parabola. Now I'm going to draw it in a dotted line first, but it's only valid starting at 1, not inclusive, so a circle here, and then extending this way upward. So the stuff that I have graphed in, oh, they want to delete my F. I'll just leave it there. All the stuff that's in red, not the dotted line, is actually part of my graph. We've graphed each piece.